Okay, guys. So I am recording this in advance because as we speak, or as I speak, no, actually, no, as you're listening, not as I speak, as you're listening, I should be halfway across Texas by now, doing some pre-college stuff that needs to be done. So chapter 15, hopefully everything worked out. And Monday we did 13, and Wednesday we did 14, and today should be Friday. You should be looking at some, well, more or less Friday. We're doing this asynchronous, so you do whatever you damn well please, but you have to look at this, right? It's dark in here. Well, it's nighttime, isn't it? What is this bright spot, right? Anyway, well, I'm going to turn off the camera in a second anyway, and use this as a tablet. So we should be on chapter 15 right now, displays and image processing. So let's get going. Let me pause here for just a second. Pause, please pause. And we're not pausing. Oh, I could pause right here. There we go. Yeah. Okay, well, hopefully the recording did stop because last time I spoke to you was about an hour ago. And I just had dinner and some conversations with my daughter. But anyway, so chapter 15, page 239, displays and image processing. Some of these concepts are pretty easy. We'll fly through those. Some of these concepts are not. So we'll go a little slower. Bistable. Well, that's basically another way of saying black and white, ebony and ivory. So black and white, these are the original ultrasound screens. They didn't have a whole lot of information. All they could say is there is an echo or there is not an echo, or there's an echo that broke the threshold and created a pixel on the screen, or the echoes that might have come from that depth were not strong enough, and so therefore they did not create an image. So black and white, obviously not a very good picture. Then we graduated to grayscale, where levels of echo intensity were able to display different levels of intensity in the, remember, the z-axis, the imaginary axis that comes straight out at you. In other words, these stronger echoes are whiter on the screen or have a higher echogenicity on the screen, whereas the weak echoes are simply displayed with darker images, zero echo, no echo, and echoic. Okay. So grayscale, many shades. Contrast. Well, contrast is, we're going to kind of come around to this concept again. They really just mentioned one sentence here for contrast on page 240, determines the range of brilliancies. Brilliancies, that's a strange word, or brightness, I guess, within the displayed image. Bistable images in which only white and black appear are high contrast. Therefore, a low contrast would be something with many shades, would be a low contrast. So let's see, range of shades. We're going to come back to this concept again because we're going to talk about ranges again. And just brightness overall, that's kind of more of a, it's almost like that's the monitor itself. Perhaps an overall gain, but when I think of brightness, you're just it's not so much the range of shades as a contrast, but all, and I'm not going to say echoes because we're just talking about the screen. Screen has pixels are either very bright or not. I'm just gonna up arrow, down arrow, bright or not. Okay, you could see images on page 240. That is all I'm gonna talk about with that. So simple concept. This concept here is a little more complex, not too bad though. The scan converter. So I gotta pause it, guys, just for a second. Okay, so a scan converter, well, it's converting something, right? That makes sense to all of you, I'm sure. Well, what do we have to convert? Now, here's the thing. When we image with an ultrasound transducer, you guys are very familiar with the fact that our beams of sound and the returning echoes are, well, let's say we're holding the transducer on top of the body. They're vertical going down. In any case, the information that's comes back to us is more of a vertical in nature. But that's not how TVs, old TVs, and even newer TVs, that's not how they write information. And so, and speaking of reading and writing, well, we'll get back into that. The information, I'm just going to put it right here, is read. Read and read. Isn't it weird how it's the same? At least unless I'm spelling it completely wrong. I know there's, anyway. It is written, I'm going to use the word written. Written over here and then read. Written as in generally in the future, in a very few, like literally minutes from now, when we talk about read and write, there's a difference between pre and post processing. In other words, a difference between what information is coming in and what we can manipulate after the fact. Some things we can, some things we cannot. That's as far as we'll go for right now. So the scan converter translates the information from the spoke format, and so spoke as in like spokes on a tire, spoke format, and into a video format, which is in the opposite direction. So notice this, we have kind of, and we'll put little arrows here, because when we create an image is read. It's read from temporary storage, and it is read from left to right on our screen. And then you could see, maybe you can't see because I made it so stinking light that I've drawn here let's see, the first yellow line comes across, and then there is a very, very light line. It's actually going to skip a line and then start again and come across. And so it is displaying this information on a left to right bias on the screen. And that is how our screens are developed over time. And this happens at a very high rate of speed. The reason why there is a skip, it goes to the end of this one, and then it skips this line and goes down to this line, is because engineers figured out that if they skip a line and then go back and do and then when they go all the way down the bottom of the screen, and then they come back up and get the second line, and then the fourth line, and the fifth and the sixth line. By alternating lines like that, engineers discovered that they can make the screen a little more smooth. But okay, what am I trying to get to here? You know, I used to, when I was in school, we had to learn a lot more about this. And thank God we don't have to now, because this technology is just kind of getting older. Although there's still scan converters, the analog scan converters. Those are very old. We're taking information in a spoke pattern. What does that mean? Well, in a pattern that's kind of up and down. You know, there's a pulse, and then there's an echo going back. And in that direction is up and down. And then we have to send that information to a screen that is written in a left to right. Now, if you think about how that is, that doesn't make a lot of sense. Well, they didn't create TV with ultrasound in mind. And so we're having to take an image that gathers information that is one line. Oh, here, you know what? Let me draw in one line, one beam line of information from a transducer. Well, that beam line of information will be like that, right? It's depth. And that's a matter of times. Your 13 microseconds per centimeter rule there. But the machine, the computer, the TV screen really doesn't create lines in that direction. I suppose they could develop something that does, but rather than developing a whole new screen that converts in another direction, they just simply run this through a scan converter. So it's not that hard to do. But if you think about this does cause a bit of an issue. If we're getting information of this red line, that scan line, this red line is basically, let's say, well, since it's on the left of the screen, we'll call it this scan line. That scan line is represented right here. But it's written onto the screen going across. So, gosh, what does that mean? If you think about it, that means that as this information is going across like this, it's putting a pixel here, and then there, and then there, and boom, boom. So it's creating the scan line, which let's see, if this is chapter 15, that means I've already spoken to you about, oh gosh, what's the terminology? What's the terminology? I gotta pause. Okay, only 2 seconds. I guess the terminology is just gonna be like, pulse line or line density or, whatever lines of information. So there, and then let's see, let's do a blue line. This would be the next line of information is here. We have a pulse and then echoes going back. Well, that's gonna be shown here on the screen. And in order to show that on the screen, these yellow lines going across are going to have to come across and show a pixel there, a pixel there, a pixel there, there. And then we have a green pulse, and that's going to show this line of information, and it's only going to show that after they're called raster lines. I don't know if you've ever heard of those. It's kind of an old term for old TVs. But, and then, that line of information is created, and so on and so forth. It seems like a very inefficient way of doing things, but, these original TVs, this is incredible technology considering what they had to work with. These original TVs were not terribly efficient in the way they set about getting information up on the screen, but they might not have been efficient, but they were wicked fast. And so you don't really see this happening. So analog transducers, or I'm sorry, analog scan converters. Well, actually, I'm going to talk about those in a little bit, about how they a little bit, I'm going to get it just a little bit in how they temporarily save information just for a second, and then they display that information and it's gone. And then we have digital scan converters, those are far more efficient, but they still work in a very linear way as well. Linear meaning they're not doing everything at once. It's kind of one thing at a time. I have a little note here in my book. Even though image is ugly with high contrast. Why is it there? Because we haven't even started talking about contrast. I'm going to put this little post-it in another page. Let me hold off on that information. So the data stored in a scan converter can be altered between writing and reading process. Where do we really talk about write and read here? We don't get into that for quite a few more pages. Read and write magnification. Okay. Well, read and write. It should be called write and read, actually, because writing is the first step. And I feel like I'm going a little bit out of order here, but the book has not helped me, honestly. Writing is the first step. Writing is the gathering of information. Once you hit freeze on your screen, writing is set in stone. You cannot change writing. You can change how you read it. What does that mean? So I'm going to go a little bit off subject here as far as page 241, chapter 15 goes. It's a little off subject, but it's still on subject, so don't get angry at me. Writing is set in stone, reading is not. Let's talk about reading. We could hit pause or freeze on our ultrasound machines and then change the gain. Well, why is that? Why can we change the gain after we've hit freeze? Because all gain is it's a display of how hard you're listening, and that could actually happen after the fact. So we can turn up our gain, make the whole screen brighter. We can turn down our gain, make the whole screen darker. And there's a number of other things we could do while the image is frozen. If you think about your smartphone, you can take a picture and then you can do all sorts of things to it, right? After the fact, you can change the color, you can change the brightness of the picture. Those are all it's called post-processing, and those are all reading the information that's already there, that's already written in different ways. You can tell your phone, I want to read this picture in sepia. In other words, I want you to display this picture in sepia because it seems cool for whatever reason. But what you can't do to that picture that you took is, what can't you do? You can't add flash. I mean, you could change the gain in a sense. You could try to pretend like there was a flash, but you cannot add a flash. The flash only occurs before. That's a right. A right, not as in like we all have rights. No, that's right as in it was written into the original data. If the flash wasn't on, it wasn't on. You cannot change that after the fact. You could. What else? If it was, I can't, for some reason I can't think right now, but I think you guys get the idea. So where am I at? The storage of the image information in the scan converters are called writing and then reading. Modern digital. Okay, let's move on to the next one. This jumps. So we go from scan converters. All right, a quick review on scan converter. It basically takes image gathered, let's just say vertically, and then images it horizontally. There has to be a scan converter because the gathering of information is not the same way that it was displayed. Okay, analog versus digital numbers. All right, well, this is pretty basic too. We're not going to get deep into this, but analog numbers are, well, I guess they're everyday numbers. Well, analogs can have a continuous range. For instance, between the 0 and 1 is an infinite number. There's an infinite number of decimal points and numbers that you can come up with between 0 and 1, which is kind of crazy to think about, but yeah, it's true. It reads in the book, a continuous range of values. For example, the weight of a person may be 164, which is what most people would say. They wouldn't say 163.998673, but they could actually weigh that, or they could weigh 164.004432, and so on. However, so that's analog. Analog, if you think of a clock, an analog clock, 12, 1, whoop, 3, 6, 9, okay. That's an analog clock. There could be any infinite number, really. I know it doesn't seem infinite, but in a kind of in a real way it is. This position of let's say the minute hand between 9 and 12, there's an infinite number of places that it could be if you really get down to small numbers. But digital numbers, we have our digital clock here. Let's see, that was my hour hand, so I guess it was 3:55 or 2:55. Who cares? It's in a digital world, it's either, now granted, it could be 3:55 if you're using your phone and point, however many seconds, but on an older clock, it was either 3:54, 3:55, 3:66. It wasn't anywhere in between. It's a little more like a digital. Digitals have discrete values. Now you might be like, well, wait a minute. You could go digital, you could digitally, on my digital calculator, create an analog number of pi, 3.14, blah, 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 blah. Numbers. But it's kind of like it's a digital representation of an analog, if that makes any sense. For example, the weight on a digital scale may be limited to whole pounds. With the digital scale, a person who actually weighs 163.12 will be reported as 163 pounds. So kind of digital is discrete. So let's just write that word. Discrete numbers. And what would we say of it? What's a continuous? Really, when we get down to it, when we think of digital numbers, we start to think of the fact that our numbers are everything can kind of go down to a computer code of zeros and ones. God, I really hate talking about this if you haven't noticed. I feel like we just kind of throw that at you and then we move on to the next one. We're going to move on to the next one. Analog scan converter. So we'll go back to those scan converters here. The analog scan converter was first type of scan converter and made of grayscale imaging possible. The analog scan converter is a funnel-shaped vacuum tube with an electron gun located within its smaller end. A stream of charged particles called electrons containing the image information are shot out of the electron gun. The larger end of the tube contains a dielectric matrix or silicon wafer. Electrons strike the matrix where they are stored. Actually, that doesn't seem 100% correct from what I've read, but that's okay. Let's draw in this vacuum tube, as it were. whatever. I can't do 3-dimensionals like that. Anyway, let me get rid of that last line. It's just in the way. Actually, I'm going to get rid of both lines. So there's a vacuum tube. Actually, when we talk about the dielectric, it's a temporary storage. We're just talking about analog storage. And I know I've said this before, but it really is amazing what engineers were able to do, was it 2020, 100 years ago? Almost 100 years ago, by creating the first televisions, first primitive televisions. And they were able to store information on the dielectric matrix. Yes, the matrix, Neo, we were all inside of it. And so information would be stored onto this matrix. And actually, let's zoom up here a little bit. And electrons, so when we talk about our very first TVs, they were really almost 100% black and white. They were what's the term? Right in front of me, bistable. But then they've turned to grayscale, in other words, black and white color TVs. And then eventually we got color, which is a whole other thing, but we're not going to talk about that, thank God. But let's say in the bistable, an electron might be shown there. Well, what is an electron? What does that mean? In the case of TV, a photon captured by the television might be shown by an electron. So there's an electron acts as the equivalent of a photon. And then, maybe there's an electron, here, an electron here, an electron here. And this information is passed through a gun, an electron gun. Let's see, let's draw a little pretty green color here. And this information, all the information here passes through a gun. And then after this gun, this electron gun, literally firing electrons, a beam of electrons. We're used to firing little pulses of sound. These guys were firing electrons, and they would go through a electromagnet. So it didn't look like this, but I figured I'd draw a magnet. And then that magnet, this is the really amazing part. They were able to manipulate the magnet. Remember, as if I taught you this already, electromagnet is magnetized when electricity runs to it. So varying the amount of electricity to it would vary the strength of the electromagnet. And there'd be there'd be electromagnets all the way around here. So there'd be here and there and there, all the way around. There'd be electromagnets, each varying its strength, and it would take this beam and it would bend it in such a way that the beam would hit, well, here, and then the beam would a microsecond later would be there, and then the beam would be there, and then the beam would be there, and it'd be going across the screen. Well, this is kind of remember what I told you before with the scan converter. It takes information that is imaged from left to right. Although I guess if I'm over here, I'm doing right to left, but that's okay. So we keep going across like this to create an image. Well, in this case, we only have 3 electrons in the matrix causing information. And so what we would see on the screen, I'm sorry, 4. We would see 4 dots on the screen. The rest of the screen would be blank. Now that would be a very basic picture, but this is basically how it is. Gun shoots in, it sends a beam across. No! I don't know what just happened. There we go. sends another beam, that goes across, sends a beam in, that goes across, but at this point, creates a pixel of information and then continues on. Next beam comes up, that comes across, creates a pixel, goes on. This beam comes across, creates a pixel, goes on. So it would be reading the information from the written. So write, read. Okay. This picture is not in the book. Probably not terribly important that you remember exactly how old-fashioned television works. I had to learn that, but you guys do not, thank God. So the analog scan, well, basically I just described an analog scan converter. The analog scan converter is a funnel-shaped electron a vacuum tube, vacuum because that's how you create an electron beam inside of a vacuum evacuated tube. In other words, no air inside of it. Stream of charged particles called electrons contain the image information and are shot out of the electron gun. The larger end of the tube contains a dielectric matrix or silicon wafer. The electrons strike the matrix where they are stored. The dielectric matrix may be thought of as a picture divided into millions of tiny dots. The stored electron charges in each bucket are read to retrieve the information. Okay, so I think that's a rather inelegant way of explaining what I already did. Not to honestly say that I was that elegant myself, but storage here, right? Storage. It happened to be temporary storage, very temporary storage, but it was written onto this dielectric wafer. So basically, we're really talking about, there's got to be like two guns, right? The first gun fires electrons to create the storage, and then that is read by imaging that onto a phosphor screen. Limitations of analog scan converters: image fade. Stored charges on the silicon wafer dissipate over time. Well, no, it's no big deal. Image flicker caused by switching between read and write modes. You cannot write and read at the same time. Instability, picture quality depends on many factors, including length of use, room temperature, and humidity. In deterioration, image degrades as the device ages. And so, yeah, I mean, I'm old enough to remember these old TVs. I used to screw with my parents' TV all the time with the little knobs hidden behind the little panel and try to mess with it all the time. And I would screw it up to the point where they had to call the TV repairman, and he'd come in and he'd blame me, and my dad would yell at me. But these TV repairmen were common because of all these problems, and they would come in and they would try to fix it as much as they can. We don't have TV repairmen anymore. I mean, we do, but kind of TVs for the most part are disposable now, because once it's broken, it's broken. Excuse me, sorry. Obviously, dinner's trying to make its way back up here. Digital scan converters use computer technology to convert images into numbers, called digitizing. The image is stored in computer memory as a series of zeros and ones. The numerical representation of the image is processed and then retranslated onto an image displayed on the monitor. So today's modern digital equipment: uniformity, consistent grayscale of quality throughout the image. Stability, it does not fade or drift. It used to be on the old computer screens, for instance, that, oh my God, the screensaver. Screensavers now are more of a novelty. A screensaver in the old days, absolutely, positively necessary, because if you left certain image or text on the screen for too long, man, it'd be burned into the screen. You'd see that for forever. It was really you could ruin the screen by leaving an image on the screen for too long. And that's where the screen savers came from. Like I said, now they're more of a novelty than anything. Durability, not affected by age or heavy use. Speed, super fast processing, and error-free accuracy. Two important elements of a digital scan are pixels and bits. Pixels and bits, pixels and bits. Gosh, I don't have anything pre-drawn for my pixels or my bits. So let's see. Pixel from the term pixel, picture element. So well, and look, we know what this means, right? Most of us understand generally what a pixel is. Here, let me pause. Okay, so if this looks similar to the dielectric right above that picture, it is. It's actually very similar. The pixels on the screen in the old televisions were, well, well, gosh, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh my God, numbers I could actually multiply. So 120 pixels on this screen. That would equate to 120 storage spaces in the dielectric. Each storage space is represented by 1 pixel. Now we're talking about primitive technology here, but that's all right. On the image from above, when we were showing that 4 locations on the dielectric were stimulated by an electron. In other words, an electron is a representation of a photon on imaging, but geez, on ultrasound, it's going to be a representation of an echo, right? Echo, photon, they're kind of the same thing in a way. You might have this, that, and that. Those pixels are stimulated, and then the rest of the screen is blank. Now, I could probably draw this in some kind of negative where the electron is bright, or the pixel is bright, representing an electron, which represents a photon. God, is that confusing or what? Or we could say that the pixel is bright because it represents an electron, which represents the echo. Now let's think about that. Let me just show that. All right, here's my little transducer here. Sound comes back, hits a piezoelectric element. The piezoelectric element creates a voltage. Why? Because that's what piezoelectric elements do. And they create this little voltage that goes back and runs into, well, I mean, there's some other things going on, but let's just say it finds its way to the dielectric and creates a memory space on that dielectric. And the dielectric is red with more electrons, because that's an electron here, right? A voltage is a number of electrons. And then it goes to the dielectric storage. Sits there for just a moment in time before it is read by an electron beam. And then that electron beam goes through the electromagnets. It is pointed at a phosphor screen, in other words, television screen. It is pointed, and as it's going through, if it finds a memory of an electron in here, it says, oh, there's an electron there. Show an electron. How do we show an electron? A pixel. How does a pixel look? Like that. Does that make sense? God, I hope that makes sense. Didn't make any sense to me. All right. Each individual box and pixel density. So spatial resolution on our screen has a lot to do with pixel density. Now, if you don't have the, well, it's just pixel density. If there's 120 pixels on your television screen, you're not going to see much. In fact, it's going to look like the image A on page 244 at the bottom. Or maybe, did I say 244? Image 15.5 or even 15.4. Those are a couple of low quality images because they don't have enough pixels to show the image well enough. But if you've ever seen pointillism, who's that artist that did pointillism? I can't think of his name, but it was pretty cool. You get up close to a television, you see the pixels, the old televisions, and I noticed as I'm sniffing now, if you sneeze onto an old television, you'd really be able to see the pixels because your spit would create tiny little lenses. So then I would spit on it. But anyway, I was a difficult kid. Okay, so pixel element, or I'm sorry, picture element is a individual dot of information, a little individual dot of temporary memory on the screen. Then we go into bits. Ooh, bits. Kibbles and bits. Pixels and bits. Pixels and bits. Okay, the bit. The word bit derived from the term binary digit. Is the smallest amount of computer memory. A bit by its nature is bistable. It is either a 0, meaning no information gathered. Well, careful how I say this. It's either a 0 or a 1. When I think of ultrasound, it's either there's an echo or there isn't. So it's either a 0 or a 1, but in computer language, that's not necessarily what it means. Binary number is a group of bits and is simply a series of zeros and ones, as I showed before. 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, whatever. Binary numbers are based on only 2 choices, 0, 1. Decimal numbers, which are used in everyday life, are based on 10 choices, 0 through 9. Why do we mention that? I don't know. It's a very simple language, this language. But if you think about it, our DNA, which creates us, is built on just 4 digits, right? 4 possibilities. And this is built on 2 possibilities, and we're still able to create supercomputers. So pretty amazing stuff. A byte, I'll have a byte of a bit is 8 bits of information equals 8 bits. So in other words, 1, 2, 3, 4, 5, 6, 7, 8 would be a byte of information. A word is equal to 16. So let's take that for one up top. 1, 0, 1, 1, 1, 0, 0, 1, 0 was 8. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That is a word of information. 16, I guess I'll write it over here. All right, 16 bits. Which is, by the way, where the term Bitcoin comes from. Each pixel shade of gray is determined by a cluster of bits assigned to it. With increasing numbers of bits per pixel, more shades of gray appear. Images with many shades of gray have better contrast resolution. Ooh, I have a hard that, I'll get back to that. I will get back to that. That has been biting me in the butt for years now. Anyway, so what does that mean? Let's say I have 1 pixel on our screen. And that pixel can be, let's see, a really light shade of, well, in this case, blue, or it could be a darker shade, or it could be even darker. Actually, it probably would have been better if I'd started with the darker and worked my way to lighter, because the darker image is a lack of information or weaker echoes. Sometimes it's purely a lack of information if it's like in a shade, like literally a shade on your screen is a lack of information. Or if it's in the middle of a fluid structure, the lack of information means that an echo didn't return from that place. So it creates a dark pixel. Let's do this. Well, let's go ahead and do this backwards. If now I have a weak echo came back at this exact location in the body, which corresponds to the echo on, I'm sorry, the pixel on the screen. And so instead of dark, we say, you know what? Actually, a weak echo came back. And then we say, well, actually, no. It was a stronger echo than that. Or no, it was even stronger. So on and so forth. When I just went backwards. I just went backwards. And I can't stop and erase this and edit it. It literally takes hours to edit my mistakes. Start over. Pixel. Let me do this intelligently and correctly this time. I apologize. This pixel originally has no echo. We could think of it as a bunch of zeros. Let's say 0 represents no echo. 0, in the case of ultrasound, basically means this pixel is dark. There's no information going to the pixel. There's no electron going to the pixel. It's just an empty pixel. And in the case of ultrasound, empty is black. And then we say, oh, but you know what? I could see where I got confused here. Yeah, I see where I see where I got myself confused. Because we're going from black to not so black. So let's say this had the slightest echo. So instead of being black on the screen, it's, gosh, barely showing up. But there's something there. This is the kind of thing where you wonder, you know, if you turn your reject up, by the way, if you turn your reject up, that's gone again. If you turn your gain down, it's gone because it's a very weak signal. And then let's see, as signals get stronger, they become brighter and brighter. Echogenic now. It started out hypoechoic or anechoic, then hypoechoic, and echogenic, and now grossly echogenic, like very echogenic now. So we went from 0, let's back up. Ooh, I like that. Okay. Oh, this is going to work out. No, it's not going to work out. No, I could verbally do this. 0. A 0. And then oh, I didn't just do that. When I drew the arrow, I screwed everything up for myself. I'm really upset with myself now. Well, that's okay. This is fine. This is fine. Zero. Actually, 0 on top of a 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 0. God, I hope this works out. 0 on top of a 0 on top of a 0 on top of a 0. What does that mean? Well, if I go instead, take away the last 0 and add a 1, well then maybe that 1 looks like this. There's a little more brightness on the screen. And now I'm going to say, you know what, it's 0, 0, 1, 1. 0, 0, 0, 1, 1. 0, 0, 0, 1, 1 means a little more. That means 2 1s were on the screen. Gets a little bit brighter still. Okay. 0, 0, 1, 1, 1. Okay. That represents an even brighter echo on the screen. And you can see where this is going. Eventually, the information in that pixel is going to be 1, 1, 1, 1, 1, 1, 1, which is by definition as echogenic as can be. That makes sense. The information coming back is now saying, and I gotta understand, we're going from electrons, we're really going from an analog system. The transducer in essence is analog. It can get a whole yowza. Oh, where'd that information come from? The transducer itself gets a continuous range from the very weakest to the very strongest of echoes. That continuous range is converted from analog, at least in our modern systems, into a digital system. So what does that mean? Let's go back to our 0s and 1s down here. When it was 0, 0, 0, 0, 0 stacked up on each other to create this pixel, that was, well, 1. It's not even hypoechoic, it was anechoic, but there was basically 0 info. In other words, 0 echoes. No echoes came back. So what the computer read from that, from what it read from a lack of electrons, in other words, a lack of information coming from the transducer, was big fat 0, 0, 0, 0, 0, 0, 0. And echoic, as dark as can be. And then we waited a little bit, and lo and behold, a weak echo came back through. A weak echo hit the transducer, creating a weak voltage. That weak voltage came up and was read as a single binary digit 1. So we had 0, 0, 0, 0, 0, 1. Still dark on the screen, but there was something there. So hypoechoic, dark, but something. And then we waited a little bit longer and the echo became a little bit stronger. And that information was turned into a voltage, and that voltage went up into the machine, and the machine said, I'm reading this now as a 00011. Well, probably still hypoechoic, but getting a little brighter, definitely there on our screen. And then the echo became stronger, creates a stronger voltage. That voltage is read as more ones, and eventually we get to the point where we cannot have any more ones. In other words, you cannot get any brighter on the screen. Echogenic. Whew, that was a lot more time than I meant to spend on that, but it's actually a hard concept. He probably wrote it down so much easier. By each pixel's shade of gray is determined by the cluster of bits assigned to it. When he says cluster of bits, this is what he's talking about. These cluster of bits, zeros and ones, with increasing numbers of bits per pixel, more shades of gray appear. Oh, and so that's the other thing. Let's just zoom in one more time, and I think we're done with this. The more zeros and ones I have, the more shades of gray I can display. So what we have here, 1, 2, 3, 4, 5. We have 5 bits of information. Not even a byte. 5 bits of information is probably going to be fairly black and white on the screen. It's not going to give us a great depth of gray scale. If, on the other hand, we had something that looked more like 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 0. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, to make it work, 11, 12, 13, 14, 15, 16. It is now a full word of information. That's going to give us a far greater possibilities of the shades of gray. And by the way, our dynamic range has increased. What? Dynamic range? That's right, I said it. Let's see, fewer shades of gray. Contrast, resolution, yeah. Images with many shades of gray have better contrast resolution. Boy, there's some disagreement out there on that. Because sometimes we say something is more contrasty when it's more black and white, but that goes exactly against this last sentence on page 245. Images with many shades of gray have better contrast resolution. We look on the next page, that's Babe Ruth. I'm sure John needed to know that because he wouldn't know that if I didn't tell him. On the left, as image A on the left has a few bits assigned to each pixel. Notice that both of these have the same number of pixels on the screen. It's not a different number of pixels. They both, let's say, have 1,000. But the depth of color, the depth of gray on these is very different. Image A has few assigned to each pixel. Image B has many assigned to each pixel. Improved contrast resolution is associated with additional bits of information. Well, yes. Oh God, I hate this part. I need to pause just to think. Okay, I just had to read that first paragraph on page 246 and cry a little bit. I can't stand it. Can't stand it. The number of determining the number of bits per pixel. Well, okay, well, I guess it's easy enough. 2 to the number of bits. So it's a power, right? It's a power of 2, or you could say 2 to the n. So how many possible shades of gray are displayed with 5 bits of memory? 2 to the 5th is the same as saying 2 times 2 times 2 times 2 times 2 is equal. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And you can see from table 15.4. Oh, well, it's interesting. Number of bits, 1. 1 bit of information, 0 or 1 is 2 to the 1, or 2 to the 1th. Number of shades of gray, 2, white or black. Number of bits is 2, then it's 2 to the 2. Number of shades of gray, 4. 3 is 8, 4 is 16, 5 is 32, 10 is 1024. So you could see, by the way, we get very quickly to a point where we cannot tell, our human eyes cannot tell the difference between the 123rd shade of gray versus the 124th shade of gray. So 10 bits of information is probably too much. So one word of information I drew earlier would be way too much. Way too many shades of gray. Okay. I could probably have drawn this in. Well, no, that's next chapter. Never mind my rambling thoughts here. Let me just squeeze this in here. We have analog and digital information, and well, the transducer itself. Firing off in this direction and receiving echoes back, creating voltages. I'm going to put an electron there. This initially actually is analog. This is analog information. It's not zeros and ones yet. It's any range, any continuous range of voltages. But then it goes to a fun little thing called a analog to digital converter. In the case of our modern equipment, then it creates these little zeros and ones, creates a digital memory. And well, that's actually, my cats are doing something, I don't know what, but it's driving me crazy. Now, this last step, a digital to analog converter, and then back to a analog screen with these raster lines being drawn across. And inside of that raster line there, we see a smiley face is being developed. This is older equipment. It went from analog to digital. And then in order to image it, to show it on the screen, it had to be, it has to go back to analog information. what I believe, did I read it somewhere? Digital signals are converted back to. But on modern equipment, our screens are actually digital. And so really, this digital to analog converter is an unnecessary step on our modern equipment. So our modern equipment just goes straight from the digital information to the screen. Doesn't it say it somewhere? Oh, next page. No, real world is analog, computer is digital. To move information from the real world, analog to digital requires a translator called an analog to digital translator. To move information back to from the digital back to analog, we need a DA converter. But modern flat panels are digital display devices. When using a digital display device, step 4, digital to analog is unnecessary. So this is step 4 here. Modern equipment, unnecessary. 1, 2, 3, 4, 5. Modern equipment, we just bypass that and go straight from 3 to, well, numbered 5, but obviously it'd be 4. Okay, pre and post processing. How did I not leave myself information for this? Information space for this. I got excited. I went straight to codec citation. Okay. Pre-processing is a manipulation of image data before storage. So we've started into this here. I need to pause to give myself some room here. Okay, I don't know how much room I need anyway, because I'm really just going to talk about this. Pre-processing, the manipulation of data before storage into the scan converter. Okay, so let's see. You can take a picture with your phone with filters on. So when you take the picture, the filter is already on. That's pre-processing. By the time the image is saved into your camera, the filter, the funny filter or whatever, has already done its work. The sonographer controls pre-processing. Pre-processing alters the image data forever and cannot be reversed or undone. Okay, with phones, we know there's a lot of pre-processing and post-processing. There's kind of a gray area there. But you know what I mean. There are certain things like filters, maybe not be the best thing, but certainly you can. The best example is actually Zoom. Zooming on your, so you can zoom before the image, and that would be pre-processing. But once you've taken that image, you can kind of magnify the image, and the wording might be zoom, but it's just magnifying a picture that's already been taken. A better example would be an actual camera with a lens and focusing that lens in on a distant point. That has to happen before you take the picture. You can't do that after the fact. So that'd be like a pre-processing. Post-processing, manipulation of image data after storage. So you could take that picture and then magnify it. That's fine. Or you can change the overall. You can change the overall gain of it. In other words, the overall brightness. That's post-processing. Since post-processing occurs after the analog to digital conversion and storage, all post-processing changes can be reversed. Post-processing changes can be reversed because just like on your camera, on your phone, there's always a revert to original picture, which I have a funny story about that, but I cannot tell that right now, which will restore all the initial numerical values of the image data because it is stored as zeros and ones. So table 15.6, pre and post-processing. Pre-processing, time gain compensation. You think we would be able to. You would think we'd be able to, but we cannot change time gain compensation after the fact. You know what, I bet you on the most modern machines we can, but on most machines we cannot. So let's just stick with that. We cannot change time gain compensation. So it is a pre-processing. However, we can change gain, overall gain. We can change the entire screen's gain, but we cannot change the curve of the gain. Log compression. Well, we haven't even spoken about what log compression is, but that is a pre-processing. Right magnification. In other words, there's two types of magnification. There's before and after, right and read magnification. Persistence. Persistence is basically how long is the information held on the screen? And so if it's held for a very short amount of time, that's short persistence. If it's held for a long amount of time, it's longer persistence. That is pre-processing only. Spatial compounding, that's a way of sending out your pulses. And you can't change the way you sent your pulses out after the fact. So that's pre. Edge enhancement, really? Edge enhancement is only pre-processing? I don't know why. Fill-in interpolation, pre-processing. Yeah, I suppose. That's something else we're going to learn about. Fill in other words, fill in stuff that ain't there, really. Post-processing. Anything you could do after the freeze is a post-process. You could invert your image from black, white to white, black, and do all that. You can magnify, but only the captured information can you magnify. Contrast variation. I think that's kind of your gray map. 3D rendering. Okay, well. Okay, so this is a good one. Magnification, I'm sorry, page 250, magnification or zoom. And you see a picture of, who's that guy again, Babe? The little red box around his head is going to show a region of interest that we're going to zoom into. Now, looks like they start on the book with read magnification. So read magnification occurs after the image data is stored. So in other words, you took the picture with your phone and you can't believe what you saw. So now you're using your fingers to spread out the picture and zoom in on it, right? That's read magnification or read zoom. So you're taking the original data that was in a smaller area and you're spreading it out to a larger area. The number of pixels stays the same, but the spatial resolution, oh, hold on, spatial resolution does not change because the number of pixels in the RI is unchanged. However, the pixels are larger in the zoomed image. Yeah, so what they're saying here is that they've taken the pixels in the region of interest and spread them out throughout the entire screen. I gotta pause here for a second. I do not like the way this is written. Could be me, it probably is. Why won't you pause? Yeah, it was me. It certainly seems like when you, I think I was thrown by figures 15.8 and 15.9, where you go from a very clear image to a grainy image. And then they have the nerve to say spatial resolution does not change. Well, it actually doesn't. It seems like it does because we're simply, and this is an exaggeration, these two pictures, but it seems like it does because we're now seeing what's already there. We're seeing the spatial resolution that's already present closer up. And so it can appear to be not as good. Now let's read magnification. As you're taking the picture, it is magnified Damn it, I just said that backwards because it's going backwards. You took the picture, now you're zooming in, magnifying a small portion of that picture. You're making that region of interest, that portion of the picture, that region of interest larger, and their spatial resolution technically does not change. Right magnification, you are magnifying before taking the actual picture, before storing the image. So the ultrasound scans, creates an image is converted from this, identifies a region of interest at that moment. So the ultrasound system scans only the region of interest and writes new data into the scan converter. That's all confusing. I skip 1 through 3 there and just go straight to 4. When you have a region of interest and you've zoomed in, the machine is only scanning the region of interest. And so it's putting all of its pixels into that picture. Right magnification, in other words, magnification while you are creating it, while you are writing it, the number of pixels or scan lines in the ROI image is greater than that in the ROI's portion of the original image. So in other words, theoretically, the increased number of pixels in the region of interest improves the spatial resolution. The pixels are the same size in both the old and the zoomed image. Pixels don't change. A pixel's a pixel. But the amount of information going into that can change. Now, here's the thing. When I say theoretically, I have tried this many times on our machines, and perhaps it's just really a testament to the quality of the image in the first place. I can't see the difference between read and write magnification on our machines, but theoretically we can. So read magnification uses old data, old as in like the data you saved just a second ago. It is post-processing, larger pixel size. No, a pixel is a pixel, but you've changed this. Yeah, okay, I see what they're saying. Pixel element. Well, let me pause and make sure I say this right, guys, because this is a tongue twister. Okay, well, a pixel is a pixel is a pixel when we're talking about the screen itself. The actual physical screen, this thing that I'm tapping on this, let's say is 1,000 pixels. It's always going to be 1,000 pixels. It's never going to change. What they're saying here is the memory of the pixels in the region of interest. So, help if I had a larger, let's say I have a larger picture here with a screwed up smiley face in there. And then I decide to come in and in read magnification, create a region of interest. That region of interest is now, once I hit, the set button, you guys know how that works. Just do it again. You guys know the set button is basically takes this little region of interest and spreads it all over the screen so that now more or less. So now those original pixels, the memory of those original pixels, what we're kind of confusing here, at least I got confused. I don't know if Edelman was confused too when he wrote it, but I certainly got confused. The memory in those pixels the zeros and ones for each pixel inside of this region of it, whoops, that region of interest has been spread out to the entire screen. So yes, in a sense, those pixels are bigger, even though a pixel is a pixel. So it does get a little confusing. So larger pixel size, yeah. So the original pixels, let's say the entire screen is 1,000 pixels and the region of interest is 100 pixels. Now those 100 pixels have been spread out, so now that they cover the entire screen. Same number of pixels as the original, yes, 100 and 100. Unchanged spatial resolution, true, because it's still the same amount of information inside each so-called pixel. Unchanged temporal resolution. Right magnification requires new data only in the region of interest. It could only happen in pre-processing. That pre-processing and right magnification are the same thing. Identical pixel size. So 1,000 pixels is our screen, our actual physical screen. And obviously I'm just making that number up, but the information is written into 1,000 pixels. So more pixels than the original ROI. Yes. That's a little confusing too. All right. I know what they're saying, but it's really. In the case of right magnification, magnifying as you're going, not after the fact, you find a region of interest and you zoom in on it. So you're using more pixels than the original region of interest. Improved spatial resolution, yes, supposedly, not on our machines, but supposedly, because you're getting more information into those smaller spaces, and then may improve temporal resolution. Yeah, it may improve temporal resolution because you have fewer beam lines to create the image. You don't need to. You only here. Let me draw that real quick. You only need these beam lines. You do not need these out here. If you don't need them, the machine's not going to create them, and it's only going to use those lines inside of the region of interest. So yeah, it can improve temporal resolution. Whew. Damn, how long has this been? A long time. My wife wants to watch TV. Let's see, it's 9 o'clock. And I'll tell you what, I'm going to stop recording and I'm going to pick up recording tomorrow. And that might be easier on you guys too. All right, guys, I'll see you tomorrow. But for you, it'll be the same day. Very weird. Very weird.